Welcome to The Calm Scientist. If you're here, it probably means you're ready to slow down, relax, and drift gently into the night with a head full of curiosity. Tonight, we're going to unravel one of the most mysterious and captivating phenomena in our universe: black holes, those cosmic enigmas that have fascinated scientists and dreamers alike for generations. We're going to peer into the very heart of darkness itself, exploring what happens when matter falls past the point of no return, and discovering truths about these gravitational monsters that might just keep you awake a little longer than planned, which would be terribly inconvenient for your plans to fall asleep. It's the kind of bedtime story only the universe could write, where space and time themselves become the main characters, dancing in ways that challenge everything we think we know about reality. Before we begin our journey to the edge of the known and beyond, if you're enjoying this gentle drift through the cosmos, I'd be wonderfully grateful if you gave the video a like and subscribed. It truly helps this peaceful little channel navigate through the vast ocean of the internet. And if you're feeling sociable tonight, let me know in the comments where in the world you're listening from and what time it is in your corner of the universe. I love picturing our little scattered constellation of sleepy minds stretching from quiet suburbs to bustling midnight cities, all connected by the same sense of wonder about the deepest mysteries of existence. This video is here to relax you, to captivate you just enough to make your thoughts drift and wander like cosmic dust. You won't need to remember any equations or specific details. Just let yourself float with me as we explore these gravitational leviathans, the physics that governs their behavior, and the absolutely mind-bending implications of what lies beyond their mysterious boundaries. And just before we embark on this cosmic journey, this video is for relaxation and education. It is not scientific advice or a substitute for professional astronomical guidance. Always look after yourself, keep your feet firmly planted on Earth, and sleep well. Let's start with the basics. What exactly is a black hole? At first glance, it sounds like the simplest thing imaginable. A region of space where gravity has become so overwhelmingly powerful that nothing, not even light itself, can escape once it crosses a certain boundary. Picture it as the ultimate cosmic vacuum cleaner, but hold that thought gently because, as it turns out, even something as conceptually straightforward as a black hole is much more slippery and strange than it seems. The story begins not with darkness, but with light, with stars. Every black hole we know of started life as a star, probably a very massive one, at least 20 or 30 times heavier than our own sun. For millions or billions of years, these stellar giants burn in a delicate balance, nuclear fusion in their cores pushing outward with tremendous force, while gravity pulls inward with equal determination. It's a cosmic standoff, a battle between the fundamental forces of nature playing out on a scale that dwarfs human comprehension. But here's where things get interesting. Unlike our sun, which will spend another 5 billion years or so in this balanced state before gently puffing off its outer layers and settling into retirement as white dwarf, these massive stars live fast and die young. When they finally run out of nuclear fuel, gravity wins the standoff in spectacular fashion. The star's core collapses catastrophically, and we mean catastrophically in the most literal sense. In less than a second, a region larger than Earth compresses down to a point smaller than the period at the end of this sentence. It's a bit like watching a skyscraper suddenly decide to become a grain of sand, except the skyscraper weighs more than our sun, and the grain of sand retains all that mass while occupying virtually no space at all. The mathematics of this collapse are so extreme that they break our normal understanding of physics. We call the result of this compression a singularity, a point where density becomes infinite and the familiar rules of space and time simply stop making sense. But wait, there's more. The singularity itself, while fascinating, isn't actually what makes a black hole black. That honour belongs to something called the event horizon, an invisible boundary surrounding the singularity where the escape velocity, the speed you'd need to break free from the gravitational pull, exceeds the speed of light. Since nothing in our universe can travel faster than light, nothing that crosses this boundary can ever come back. Think of it as the ultimate one-way street, except instead of leading to another neighbourhood, it leads to a region of space-time so warped and twisted that our best theories can barely describe what happens there. The event horizon isn't a physical surface like the ground beneath your feet or the walls of your room. You couldn't stand on it or touch it. It's more like an invisible line in space, a point of no return defined purely by the geometry of space-time itself. Meanwhile, the name event horizon is rather poetic when you think about it. It's the horizon beyond which events can never be observed from the outside universe. Just as you can't see beyond the horizon when you're standing on a beach, an outside observer can never see beyond the event horizon of a black hole. But there's something quietly profound about this limitation. It suggests that the universe has built-in boundaries, natural limits to what can be known or observed even in principle. Let's take a closer look at what these gravitational monsters actually look like. If you could somehow approach a black hole, and we definitely don't recommend trying this at home, you wouldn't see a black sphere sitting in space like a cosmic bowling ball. Instead, you'd see something far more subtle and strange. The black hole itself would appear as a perfectly circular region of absolute darkness against the star-filled background of space. But this darkness would be surrounded by one of the most beautiful and terrifying sights in the universe. Matter falling into the black hole, dust, gas, sometimes entire stars torn apart by tidal forces, forms what astronomers call an accretion disk. This disk of material spirals inward toward the event horizon, heating up to millions of degrees as gravitational forces compress and accelerate it. The result is a brilliant, swirling maelstrom of light that can outshine entire galaxies. It's as though the universe's ultimate destroyer has become its most spectacular artist, painting with plasma and radiation on a canvas of warped space-time. Speaking of warped space-time, there's something even stranger about how black holes interact with the fabric of reality itself. Einstein showed us that massive objects don't just sit in space like marbles on a table. They actually bend and curve space-time, creating wells and valleys in the very foundation of reality. A black hole represents the extreme limit of this bending, a place where space-time curves so dramatically that it essentially closes in on itself. Imagine trying to walk up an increasingly steep hill, where each step requires more energy and takes you higher up the slope. Now imagine that the hill becomes so steep that it actually curves back on itself, creating a slope so vertical that no amount of energy could carry you over the top. That's roughly analogous to what happens to space-time around a black hole. The curvature becomes so extreme that not even light travelling at the cosmic speed limit can climb out of the gravitational well. But there's so much more to explore about these remarkable objects. For instance, black holes come in different varieties, each with its own peculiar characteristics and behaviours. The most common type, formed from collapsed stars, are called stellar mass black holes, and they typically weigh in at somewhere between 3 and 20 times the mass of our Sun. But lurking at the centres of most galaxies, including our own Milky Way, are supermassive black holes that can contain millions or even billions of times the mass of the Sun. How does something become that massive? It's a question that has puzzled astronomers for decades. These supermassive giants are so enormous that they couldn't have formed from the collapse of even the most massive stars. Instead, they likely grew over billions of years, feeding on gas, dust, and occasionally other black holes, gradually accumulating mass until they became the gravitational anchors around which entire galaxies revolve. There's something deeply fascinating about the relationship between these supermassive black holes and their host galaxies. Far from being cosmic destroyers that simply consume everything in their path, they appear to play a crucial role in regulating star formation and galaxy evolution. The jets of high-energy particles they sometimes produce can heat up and disperse the gas needed for new stars to form, effectively controlling the growth rate of their host galaxy. It's as though these ultimate consumers have become cosmic gardeners, pruning and shaping the very galaxies they inhabit. Let's delve deeper into one of the most mind-bending aspects of black holes, their effect on time itself. This is where things get truly strange, where our everyday experience of temporal flow meets the relativistic reality of extreme gravity. According to Einstein's theory of general relativity, time runs more slowly in stronger gravitational fields. Near a black hole, where gravity is at its most intense, this effect becomes dramatic beyond imagination. If you were unfortunate enough to fall toward a black hole while a friend watched from a safe distance, something remarkable and disturbing would happen. From your perspective, falling freely toward the event horizon, everything would seem relatively normal, at least initially. You might notice the stars behind you shifting color as light from the outside universe becomes increasingly blue-shifted, compressed by the intense gravitational field. The black hole itself might begin to fill more and more of your view, though you'd never actually see the event horizon as a distinct boundary. But from your distant friend's perspective, watching through a powerful telescope, your journey would appear very different. As you approach the event horizon, you would seem to slow down dramatically. The light from your body, fighting to escape the ever stronger gravitational field, would become redder and dimmer. To your friend, you would appear to freeze just at the edge of the event horizon, your image fading gradually until it disappeared entirely. According to their clocks, you would never actually cross the event horizon. You'd be caught forever at the moment of crossing, like a fly trapped in amber. This is one of the most profound puzzles in physics, known as the information paradox or the firewall paradox. From the outside universe's perspective, nothing ever actually falls into a black hole. Matter and energy approach the event horizon and then seem to stop, their information somehow encoded on the black hole's surface. But from the perspective of someone falling in, they cross the event horizon and continue inward toward the singularity. Both perspectives are equally valid according to general relativity, yet they seem to describe completely different realities. It reminds us that our intuitive understanding of time as a universal constant, ticking away at the same rate everywhere in the universe, is nothing more than a convenient illusion. Near black holes, time becomes fluid, stretching and compressing like taffy, creating paradoxes that challenge our most basic assumptions about cause and effect, about what it means for events to happen in sequence. Here's where things get even more interesting. In 1974, a brilliant physicist named Stephen Hawking made one of the most surprising discoveries in the history of science. Using the principles of quantum mechanics, the theory that describes the behavior of particles at the smallest scales, he calculated that black holes shouldn't be perfectly black after all. Instead, they should emit a faint glow of radiation, gradually evaporating over time like cosmic ice cubes. This Hawking radiation arises from quantum fluctuations near the event horizon. In the strange world of quantum mechanics, empty space isn't actually empty. It's filled with pairs of virtual particles that spontaneously appear and disappear, borrowing energy from the vacuum and paying it back so quickly that the transaction goes unnoticed. But near the event horizon of a black hole, something remarkable happens. Sometimes, one particle from such a pair falls into the black hole while the other escapes, turning the virtual particles into real ones and causing the black hole to lose a tiny amount of mass in the process. The implications of this discovery are staggering. It means that black holes aren't eternal. Given enough time, they will evaporate completely, returning their mass to the universe as a shower of elementary particles and radiation. For a black hole with the mass of our Sun, this process would take longer than the current age of the universe by a factor of trillions upon trillions. But smaller black holes would evaporate more quickly, and in the final moments of a black hole's existence, it would release all its remaining energy in a brilliant flash that would make nuclear explosions look like birthday candles. But wait, there's more to this quantum story. Hawking radiation creates what might be the deepest puzzle in modern physics. According to the principles of quantum mechanics, information cannot be destroyed. Every particle, every quantum state, every bit of information that falls into a black hole should somehow be preserved and eventually returned to the universe when the black hole evaporates. But Hawking radiation appears to be completely random, containing no information about what fell into the black hole in the first place. This creates the black hole information paradox. If information is truly lost when it falls into a black hole, then quantum mechanics is wrong. But if information is somehow preserved and encoded in the Hawking radiation, then our understanding of what happens at event horizons is fundamentally flawed. Some of the brightest minds in physics have spent decades wrestling with this puzzle, proposing solutions that range from the elegant to the bizarre. One possibility is that information is indeed encoded in Hawking radiation, but in such a subtle way that we haven't yet learned how to decode it. Another suggests that the smooth event horizons predicted by general relativity don't actually exist, replaced instead by firewalls of high-energy particles that would incinerate anything attempting to cross them. Still others propose that the information paradox reveals something profound about the nature of space and time themselves, suggesting that our familiar three-dimensional reality might be nothing more than a hologram projected from information encoded on distant surfaces. Let's turn our attention to what might actually happen to someone or something that crosses the event horizon and continues inward toward the singularity. This journey into the heart of a black hole is one of the most extreme and bizarre experiences imaginable, a voyage into a realm where the familiar laws of physics are pushed to their absolute limits and beyond. As an object falls deeper into the black hole, the gravitational field becomes increasingly non-uniform. The force pulling on the parts of the object closest to the centre becomes significantly stronger than the force on the parts further away. This difference in gravitational force is called a tidal effect, and near a black hole it becomes strong enough to stretch any object like a piece of taffy. Imagine being pulled apart vertically while being squeezed together horizontally, stretched into an ever thinner noodle-like shape. Physicists have given this process the rather undignified name of spaghettification, but the reality would be far from amusing for anyone experiencing it. Long before you could contemplate the philosophical implications of your situation, the tidal forces would overcome the molecular bonds holding your body together, reducing you to a stream of individual atoms spiraling inward toward the central singularity. But let's consider what might happen to those atoms as they continue their journey inward. According to general relativity, they would eventually reach the singularity itself, the point of infinite density and curvature at the very centre of the black hole. Here, all the matter that has ever fallen into the black hole is compressed into a region of zero volume, creating conditions so extreme that our current theories of physics simply break down and cease to provide meaningful predictions. The singularity represents what physicists call a breakdown of predictability. It's not just that we don't know what happens there, it's that the very concept of what happens becomes meaningless. Time and space, the stage upon which all physical processes play out, become so distorted that they lose their familiar properties. Some theorists suggest that the singularity might be a gateway to other regions of space-time, perhaps even other universes entirely, but these ideas remain highly speculative. This brings us to one of the most fascinating and controversial ideas in black hole physics: the notion that the interior of a black hole might be far stranger and more complex than simple collapse to a singularity. Some researchers have proposed that quantum effects, which become increasingly important as matter is compressed to smaller and smaller scales, might prevent the formation of a true singularity entirely. One such idea is the fuzzball hypothesis, which suggests that what we think of as a black hole is actually a complex quantum object with structure extending throughout the region inside the event horizon. According to this theory, information falling into a black hole doesn't disappear or reach a singularity, but becomes encoded in the quantum structure of the fuzzball itself. It's a beautiful idea that would resolve the information paradox while preserving both quantum mechanics and general relativity, though proving or disproving it remains extraordinarily challenging. Meanwhile, other researchers have explored the possibility that black holes might serve as cosmic recycling centers, processing matter and information in ways we're only beginning to imagine. Loop quantum gravity, an attempt to merge quantum mechanics with general relativity, suggests that the singularity might be replaced by a quantum bounce, where the collapsing matter reaches a minimum size and then begins to expand again, potentially creating a new universe on the other side of the black hole. Speaking of other universes, let's explore one of the most mind-boggling ideas to emerge from black hole physics: the concept of black hole complementarity. This principle, developed to address the information paradox, suggests that reality itself might be fundamentally ambiguous when it comes to black holes. According to an outside observer, information never actually enters a black hole but remains encoded on its surface forever. But according to someone falling in, information definitely crosses the event horizon and continues toward the interior. Both descriptions are equally valid and equally real, even though they seem to contradict each other. It's as though the universe itself can't decide on a single version of events, so it maintains multiple realities simultaneously. This idea challenges our most basic assumptions about objective reality, suggesting that what we think of as truth might be observer-dependent in the most fundamental way possible. This observer dependence extends to other aspects of black hole physics as well. The temperature and entropy of a black hole, fundamental properties that should seem objective and measurable, depend crucially on the reference frame of the observer. A freely falling observer crossing the event horizon would measure zero temperature for the Hawking radiation, while a distant observer would detect a thermal glow. It's as though black holes exist in multiple states simultaneously, revealing different aspects of themselves to different observers. But there's so much more to explore about the quantum nature of these cosmic enigmas. Recent developments in theoretical physics have suggested that black holes might be the key to understanding some of the deepest mysteries of quantum mechanics itself. The holographic principle, born from black hole thermodynamics, proposes that all the information contained within any volume of space can be encoded on the boundary of that volume. Think of it like a hologram on a credit card, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. According to the holographic principle, our familiar three-dimensional reality might actually be encoded on a distant two-dimensional surface, with black holes serving as the cosmic laboratories where this encoding becomes most apparent. This leads to the remarkable possibility that black holes aren't just objects in space-time, but are actually fundamental to the structure of space-time itself. Some theorists have proposed that space-time might emerge from quantum entanglement between microscopic degrees of freedom, with black holes representing regions where this entanglement becomes so strong that it warps the geometry of reality. Let's delve deeper into the relationship between black holes and quantum entanglement, one of the strangest phenomena in quantum mechanics. When two particles become entangled, they remain mysteriously connected regardless of the distance separating them. Measuring the properties of one particle instantly affects the properties of its partner, even if they're on opposite sides of the universe. Recent research has suggested that the interior and exterior of black holes might be connected by quantum entanglement in profound and unexpected ways. The ER equals PR conjecture, named after Einstein, Rosen, Podolsky, and Rosen, proposes that every quantum entanglement corresponds to a microscopic wormhole connecting distant regions of space-time. If this idea is correct, then black holes might be riddled with tiny passages that connect their interiors to the outside universe in ways that preserve information while maintaining the integrity of the event horizon. It's a breathtaking idea that would transform our understanding of both black holes and quantum mechanics. Instead of being isolated regions cut off from the rest of the universe, black holes would be intimately connected to the cosmic web through quantum threads that transcend the normal limitations of space and time. The information that appears to be lost when matter falls into a black hole would actually be preserved in these quantum connections, accessible to the outside universe through the mysterious channels of entanglement. Meanwhile, the study of black hole mergers has opened up entirely new ways of exploring these gravitational monsters. When two black holes spiral into each other and merge, they create ripples in space-time itself, gravitational waves that propagate outward at the speed of light. These waves carry information about the masses, spins, and orbital characteristics of the merging black holes, allowing us to study these objects in ways that would be impossible through light alone. The detection of gravitational waves by facilities like LIGO has revealed a universe far more dynamic and violent than we ever imagined. Black hole mergers occur regularly throughout the cosmos, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. Each merger creates a new, larger black hole, while sending ripples through space-time that carry the news of this cosmic collision to distant observers. These gravitational wave observations have also revealed surprising populations of black holes that we never knew existed. Intermediate mass black holes, weighing in at hundreds of times the mass of the Sun, appear to be more common than previously thought. Some of these might be the seeds from which supermassive black holes grow, while others might represent an entirely new class of cosmic objects with their own unique formation mechanisms and evolutionary pathways. Let's explore the possibility that black holes might not be the cosmic monsters we've imagined, but could actually be essential for the structure and evolution of the universe itself. The relationship between supermassive black holes and their host galaxies is so tight that some astronomers have suggested they evolved together, each shaping the other's development over billions of years. The jets and outflows from actively feeding supermassive black holes can extend for millions of light years, carrying energy and momentum far beyond the boundaries of their host galaxies. These jets can trigger star formation in some regions, while suppressing it in others, sculpting the large-scale structure of the universe in ways we're only beginning to understand. It's as though these gravitational giants serve as cosmic architects, designing and building the very galaxies they inhabit. But there's something even more profound about the role black holes might play in cosmic evolution. Some theories suggest that black holes could be cosmic reproduction mechanisms, spawning new universes through processes we can barely imagine. If the interior of a black hole does indeed lead to a region of expanding space-time, then every black hole might give birth to an entire cosmos, complete with its own laws of physics and its own potential for life and complexity. This idea leads to the remarkable possibility that our own universe might have been born from a black hole in some parent universe, and that the black holes we observe might be giving birth to countless baby universes even as we speak. It's a fractal cosmos where each level of reality contains the seeds of the next, with black holes serving as the cosmic bridges between different layers of existence. The implications for life and consciousness are staggering. If black holes do spawn new universes, then the formation of these gravitational giants might be one of the most important evolutionary processes in the cosmos, spreading the potential for complexity and awareness throughout an infinite hierarchy of realities. Every massive star that collapses to form a black hole might be planting the seed for countless future civilizations in universes yet to be born. Speaking of consciousness, there's a fascinating connection between black hole physics and information theory that might shed light on the nature of awareness itself. The entropy of a black hole, a measure of the information it contains, is proportional to the area of its event horizon rather than its volume. This area law has profound implications for how information can be stored and processed in physical systems. Some researchers have speculated that consciousness might be related to information integration in complex systems, and that the holographic principle emerging from black hole physics might provide clues about how awareness emerges from the quantum substrate of reality. If our three-dimensional experience is indeed encoded on a two-dimensional surface, then consciousness itself might be a holographic phenomenon emerging from information processing at the boundaries of space-time. This connects to deeper questions about the relationship between mind and matter, between subjective experience and objective physical processes. Black holes, as the ultimate laboratories for studying the limits of physical law, might hold the key to understanding how consciousness arises from the quantum mechanical foundation of reality. Let's turn our attention to the practical implications of black hole research for technology and human civilization. While black holes themselves are far too dangerous and distant to serve as energy sources or transportation systems, the theoretical insights gained from studying them have already revolutionized our understanding of physics and could lead to breakthrough technologies in the future. The study of black hole thermodynamics has deepened our understanding of the relationship between information, energy, and entropy. These insights are already being applied to the development of more efficient computer algorithms and data storage systems. The holographic principle, born from black hole physics, is inspiring new approaches to quantum computing and artificial intelligence. Gravitational wave detectors, built to study black hole mergers, represent some of the most sensitive scientific instruments ever constructed. The technologies developed for these detectors, from ultra-stable laser systems to vibration isolation mechanisms, are finding applications in fields ranging from precision manufacturing to geological monitoring. But perhaps the most profound impact of black hole research lies in its transformation of our philosophical understanding of reality. These objects have forced us to confront the limits of knowledge, the observer dependence of truth, and the deep connections between information, entropy, and the structure of space-time itself. Let's delve deeper into some of the more exotic types of black holes that theorists have proposed. Rotating black holes, called Kerr black holes after the mathematician who first described them, possess additional complexities that make them even stranger than their non-rotating cousins. The rotation drags space-time itself around the black hole, creating a region called the ergosphere, where nothing, not even light, can remain stationary relative to distant observers. Within the ergosphere, particles and light rays are forced to rotate along with the space-time, but they can still escape if they have enough energy directed outward. This creates the remarkable possibility of extracting energy from a rotating black hole through a process called the Penrose mechanism. By dropping an object into the ergosphere and allowing it to split apart with one piece falling into the black hole and the other escaping, it's theoretically possible to extract more energy from the escaping piece than was originally invested in the object. It's as though rotating black holes are cosmic flywheels, storing rotational energy that can be tapped by sufficiently advanced civilizations. Some futurists have speculated that intelligent species might eventually learn to harvest energy from black holes in this way, using them as power sources for galaxy-spanning civilizations. The amount of energy stored in the rotation of a supermassive black hole is truly staggering, potentially enough to power an advanced civilization for billions of years. Meanwhile, electrically charged black holes, called Reissner-Nordström black holes, possess their own unique characteristics. Unlike rotating black holes, which are common in the universe, charged black holes are extremely rare because any net electrical charge would quickly be neutralized by attracting oppositely charged particles from the surrounding space. But in the theoretical realm, charged black holes reveal fascinating insights about the relationship between gravity and electromagnetism. These charged black holes can possess what are called naked singularities, regions where the singularity at the center is not hidden behind an event horizon. If such objects could exist in nature, they would allow us to observe directly the breakdown of physical law at the singularity, potentially revealing new physics beyond our current theories. However, the cosmic censorship hypothesis suggests that nature abhors naked singularities and always clothes them in event horizons, protecting the rest of the universe from the unpredictable behavior that might emerge from these regions where physical law breaks down. Let's explore one of the most speculative but tantalizing possibilities in black hole physics, the idea that these objects might serve as portals to other regions of space-time. The mathematical solutions to Einstein's equations that describe black holes often include white holes, hypothetical objects that would be the time reverse of black holes. While black holes allow matter and energy to fall in but never escape, white holes would do the opposite, spewing matter and energy outward while never allowing anything to enter. The connection between black holes and white holes leads to the concept of wormholes, theoretical tunnels through space-time that could connect distant regions of our universe or even bridge to entirely separate universes. If wormholes exist, they might be created when black holes and white holes are connected through regions of space-time with exotic properties that we don't yet understand. Some theories suggest that the Big Bang itself might have been a white hole, the other end of a black hole that formed in a previous universe or in a different region of a larger multiverse. This would mean that our entire observable cosmos emerged from the interior of a black hole, making us all children of these gravitational giants in the most literal sense possible. The idea of traversable wormholes, passages through space-time that could allow travel between distant locations without crossing the intervening space, has captivated both scientists and science fiction writers for decades. While the physics of such objects remains highly speculative, recent research has suggested that quantum entanglement might provide a mechanism for creating and stabilizing wormhole connections. But there's something deeply poetic about the possibility that black holes, which appear to be the universe's ultimate isolators, cutting regions of space-time off from the rest of reality, might actually be cosmic connectors, linking distant parts of the universe through hidden channels that transcend our ordinary experience of space and time. Speaking of poetry, let's consider the aesthetic and philosophical dimensions of these cosmic phenomena. Black holes represent some of the most extreme and beautiful objects in the universe, places where the familiar gives way to the utterly alien, where the laws of physics are pushed to their breaking point and beyond. They embody both destruction and creation, endings and beginnings, isolation and connection. There's something deeply moving about the way these objects challenge our most basic assumptions about reality. They force us to confront the limits of knowledge, the relativity of truth, and the profound mystery of existence itself. In their presence, the comfortable certainties of everyday life dissolve, replaced by questions that stretch the boundaries of human understanding. The mathematical beauty of black hole solutions to Einstein's equations rivals the greatest works of art in its elegance and profundity. The Schwarzschild solution, describing a non-rotating black hole, can be written in just a few lines of mathematics, yet it encodes an entire cosmos of strange and wonderful phenomena. The Kerr solution, describing rotation, adds layers of complexity that reveal new depths of meaning with each level of analysis. These mathematical descriptions are not just abstract symbols on paper, but represent genuine insights into the nature of reality itself. They reveal a universe far stranger and more wonderful than our everyday experience suggests, a cosmos where time and space are fluid, where causality becomes ambiguous, and where the boundary between existence and non-existence blurs beyond recognition. Let's delve deeper into the observational evidence for black holes and how we've learned to detect and study these invisible objects. Since black holes don't emit light themselves, astronomers have had to develop ingenious indirect methods for finding and characterizing them. The key is to look for their gravitational effects on surrounding matter and space-time. Binary systems, where a normal star orbits a compact object, provide some of the best evidence for stellar mass black holes. By measuring the orbital motions of the visible star, astronomers can calculate the mass of its invisible companion. When that mass exceeds about 3 times the mass of the Sun, the theoretical upper limit for neutron stars, the invisible object is almost certainly a black hole. In some cases, matter from the normal star flows toward the black hole, forming an accretion disk that heats up and glows brilliantly in X-rays. These X-ray binaries have provided detailed information about black hole properties and behavior, allowing astronomers to test predictions of general relativity in the strong field regime where gravitational effects are most pronounced. The supermassive black holes at galaxy centers reveal themselves through their effects on nearby stars and gas. At the center of our own Milky Way, astronomers have tracked individual stars orbiting the supermassive black hole called Sagittarius A star for decades, watching them follow elliptical paths that match the predictions of general relativity with exquisite precision. Some of these stars approach within a few hundred times the distance between Earth and the Sun, reaching speeds of thousands of kilometers per second at their closest approach. But perhaps the most dramatic evidence for black holes came with the first direct image of a black hole's event horizon, captured by the Event Horizon Telescope in 2019. This image, showing the supermassive black hole at the center of the galaxy M87, revealed the characteristic shadow of the event horizon, surrounded by a bright ring of glowing matter. It was humanity's first direct glimpse of one of these cosmic monsters, confirming decades of theoretical predictions about their appearance and behavior. The image showed not just a static black circle, but revealed dynamic processes around the black hole, with matter flowing in complex patterns determined by the interplay of gravity, magnetism, and relativistic effects. Subsequent observations have revealed that the brightness and structure of the emission change over time, providing insights into the physics of matter in extreme gravitational fields. Meanwhile, gravitational wave astronomy has opened an entirely new window into the black hole universe. The LIGO and Virgo detectors have now observed dozens of black hole mergers, revealing a population of these objects that was largely unknown before gravitational wave detection became possible. These observations have shown that black hole mergers are relatively common events, occurring somewhere in the observable universe every few minutes. Each gravitational wave detection provides a wealth of information about the merging black holes, including their masses, spins, and the dynamics of their final spiral into each other. The waves themselves carry information about the nature of gravity in the strong field regime, allowing physicists to test general relativity in conditions that cannot be reproduced in terrestrial laboratories. The most massive black hole merger detected so far created a final black hole of about 150 solar masses, releasing more energy and gravitational waves than all the stars in the observable universe emit in light. The merger lasted only a fraction of a second, but in that brief moment, space-time itself rang like a bell, sending ripples across the cosmos that encoded the story of this cosmic collision. Let's explore the connection between black holes and the large-scale structure of the universe. Recent observations have revealed that supermassive black holes are not randomly distributed throughout space, but are intimately connected to the cosmic web, the vast network of dark matter filaments that provides the scaffolding upon which galaxies form and evolve. The most massive galaxies, which harbour the most massive black holes, tend to sit at the intersections of these dark matter filaments, in regions where matter has been flowing together for billions of years. This suggests that the formation of supermassive black holes is tied to the fundamental processes that shape the structure of the universe on the largest scales. computer simulations of cosmic evolution have revealed that black holes play active roles in regulating star formation and galaxy growth throughout the universe's history. The energy released when matter falls into black holes can heat and disperse the gas needed for star formation, creating what astronomers call feedback that prevents galaxies from growing too large too quickly. This feedback process appears to be crucial for explaining why the universe looks the way it does today. Without it, simulations produce galaxies that are far too massive and contain far too many stars compared to what we actually observe. The black holes act as thermostats, regulating the temperature of gas in and around galaxies and controlling the rate at which new stars can form. But there's something even more profound about the role of black holes in cosmic evolution. Some theories suggest that the formation of the first supermassive black holes in the early universe might have been crucial for creating the conditions necessary for complex structure formation. These primordial black holes could have served as seeds around which the first galaxies assembled, providing the gravitational anchors that allowed matter to coalesce into the patterns we see today. The relationship between black hole growth and galaxy evolution extends across cosmic time, creating what astronomers call coevolution. As galaxies merge and grow, their central black holes eventually merge as well, creating even more massive objects that can influence star formation over even larger volumes of space. This process has been ongoing for billions of years, gradually building up the population of supermassive black holes we observe today. Let's delve deeper into the quantum mechanics of black holes and explore how these classical objects of general relativity interact with the quantum world. The marriage of quantum mechanics and black hole physics has produced some of the most profound and puzzling results in theoretical physics, challenging our understanding of information, causality, and the nature of reality itself. One of the most remarkable discoveries is that black holes have temperature and entropy, thermodynamic properties that were traditionally associated only with large collections of particles. The temperature of a black hole is inversely proportional to its mass, meaning that smaller black holes are actually hotter than larger ones. A black hole with the mass of our Sun would have a temperature of only about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. But a microscopic black hole, if such things could exist, would be incredibly hot, potentially hot enough to evaporate in a brilliant flash of radiation. This creates the paradoxical situation where the largest, most massive black holes in the universe are among the coldest objects in existence, while the smallest would be among the hottest. The entropy of a black hole, a measure of the amount of information it contains, is proportional to the area of its event horizon rather than its volume. This area law for entropy was one of the first hints that something fundamental about information storage in physical systems needed to be reconsidered. In normal matter, entropy typically scales with volume, but black holes seem to follow different rules entirely. This led to the development of the holographic principle, one of the most revolutionary ideas in modern physics. According to this principle, all the information contained within any volume of space can be encoded on the boundaries of that volume, much like a hologram encodes three-dimensional information on a two-dimensional surface. If this principle is correct, then our familiar three-dimensional experience of reality might be nothing more than a projection from information encoded on distant surfaces. Meanwhile, the study of black hole microstates has revealed deep connections between gravity and quantum field theory. String theory, one of the leading candidates for a theory of quantum gravity, suggests that black holes are not featureless objects but possess incredibly complex internal structures made up of fundamental strings and branes vibrating in higher dimensional spaces. According to string theory, the entropy of a black hole arises from the vast number of different ways these microscopic components can be arranged while producing the same macroscopic properties. It's as though each black hole is like a vast library containing enormous amounts of information, but written in a language so foreign to our experience that we can only glimpse its contents indirectly. The ADES-CFT correspondence, a remarkable duality discovered in string theory, suggests that the physics inside certain types of black holes is exactly equivalent to the physics of quantum field theories, living on the boundaries of space-time. This means that the complex dynamics occurring in the interior of a black hole might be perfectly described by simpler theories operating on lower dimensional surfaces. This correspondence has profound implications for our understanding of quantum gravity and the nature of space-time itself. It suggests that space-time might be emergent, arising from more fundamental quantum mechanical processes rather than being a basic feature of reality. Black holes, in this view, are not objects embedded in space-time, but are manifestations of the underlying quantum information processing that gives rise to our experience of space and time. Let's explore the possibility that black holes might be conscious or possess some form of information processing capability. This might sound like science fiction, but some serious physicists have speculated about the relationship between consciousness and information integration in complex systems. If consciousness is indeed related to information processing, then black holes, as the ultimate information processing systems in the universe, might possess some form of awareness. The integrated information theory of consciousness suggests that awareness arises from the integration of information across complex networks. Black holes, with their vast entropy and complex internal structure, certainly qualify as complex information processing systems. Some researchers have even calculated that a supermassive black hole might possess more integrated information than the human brain, raising the tantalizing possibility that these cosmic giants might be conscious in ways we can barely imagine. Of course, this remains highly speculative, and consciousness might require specific types of information processing that black holes don't possess. But the idea highlights how our growing understanding of black hole physics is forcing us to reconsider fundamental questions about the nature of mind, matter, and information in the universe. Speaking of information, let's delve deeper into the black hole information paradox and some of the proposed solutions that have emerged from decades of research. This paradox strikes at the heart of our understanding of both quantum mechanics and general relativity, revealing tensions between these two pillars of modern physics that we're still struggling to resolve. The paradox arises because quantum mechanics demands that information cannot be destroyed, while classical general relativity suggests that anything falling into a black hole is lost forever, when the black hole eventually evaporates through Hawking radiation. If information is indeed destroyed, then quantum mechanics is violated. But if information is preserved, then our understanding of black hole horizons must be fundamentally wrong. One proposed solution is the holographic storage of information on the black hole's event horizon. According to this idea, information falling into a black hole doesn't actually cross the horizon, but remains encoded on its surface in incredibly fine detail. The Hawking radiation would then carry this information back out as the black hole evaporates, preserving quantum mechanics while maintaining the basic structure of general relativity. But this solution creates its own puzzles. If information never actually enters a black hole, then what happens to objects that appear to fall in? From the perspective of outside observers, matter approaches the horizon and then seems to spread out over its surface, creating what physicists call a stretched horizon. But from the perspective of infalling matter, the journey continues smoothly through the horizon toward the interior. This leads to the black hole complementarity principle, which suggests that these two descriptions are both correct but apply to different observers. The universe maintains multiple consistent descriptions of reality simultaneously, with each observer experiencing their own version of truth. It's a deeply unsettling idea that challenges our notion of objective reality and suggests that the universe might be fundamentally observer-dependent. Another proposed solution to the information paradox is the firewall hypothesis, which suggests that the smooth event horizons predicted by general relativity don't actually exist. Instead, quantum effects create a wall of high-energy radiation just outside the horizon that would incinerate anything attempting to cross it. This preserves information by preventing it from ever entering the black hole in the first place, but it requires abandoning the equivalence principle, one of the founding principles of general relativity. More recently, some physicists have proposed that the paradox might be resolved through quantum error correction, the same principles used to protect information in quantum computers. According to this idea, the universe itself might operate like a quantum computer, with black holes serving as cosmic hard drives that store and process information in ways that preserve it even under extreme conditions. Let's explore the connection between black holes and the arrow of time, one of the deepest mysteries in physics. Why does time seem to flow in only one direction, from past to future, when the fundamental laws of physics are mostly time-symmetric? Black holes might provide crucial insights into this puzzle through their relationship with entropy and the second law of thermodynamics. The formation of a black hole represents one of the most dramatic increases in entropy possible in the universe. When matter collapses to form a black hole, its entropy increases enormously, from the relatively low entropy of organized stellar matter to the enormous entropy associated with the black hole's event horizon. This process is irreversible in any practical sense, providing a clear arrow of time pointing from the organized past toward the disorganized future. But the evaporation of black holes through Hawking radiation creates a puzzle for the arrow of time. If black holes eventually evaporate completely, returning their matter to the universe as thermal radiation, then the final state might have lower entropy than the initial state, seemingly violating the second law of thermodynamics. This suggests that our understanding of entropy and time's arrow in the presence of black holes is still incomplete. Some theories propose that the evaporation process doesn't actually reduce entropy, but transforms it in subtle ways that we don't yet understand. The information that was encoded in the original stellar matter might be preserved in the correlations between Hawking radiation particles, maintaining the overall entropy of the system even as the black hole disappears. Others suggest that black hole evaporation might indeed represent a reversal of time's arrow, with the final stages of evaporation essentially running the collapse process in reverse. This would mean that the universe contains regions where time flows backward relative to our experience, creating isolated pockets where cause and effect operate in reverse order. Meanwhile, the relationship between black holes and quantum entanglement continues to reveal new insights into the nature of space-time itself. Recent research has suggested that the connectivity of space-time might emerge from quantum entanglement between microscopic degrees of freedom, with black holes representing regions where this entanglement becomes so strong that it creates the curved geometry we observe. This idea, known as the entanglement genesis of space-time, suggests that space and time are not fundamental features of reality but emergent properties that arise from more basic quantum mechanical processes. Black holes, as the most extreme examples of space-time curvature, might be cosmic laboratories where we can study the transition between the quantum realm of fundamental particles and the classical realm of curved space-time. The ER equals PR conjecture takes this idea even further, proposing that every quantum entanglement corresponds to a microscopic wormhole connecting distant regions of space-time. If this is correct, then the interior of a black hole might be riddled with tiny passages that connect it to the outside universe through quantum channels that transcend ordinary space and time. These quantum wormholes would be far too small to allow the passage of ordinary matter, but they might provide channels through which information can flow between the interior and exterior of black holes. This could resolve the information paradox while preserving both the smooth horizons of general relativity and the information conservation of quantum mechanics. Let's delve deeper into the role of black holes in the cosmic recycling of matter and energy. These gravitational giants don't just consume matter, they transform it, processing the basic building blocks of reality and potentially creating new forms of organization and complexity that wouldn't exist otherwise. The accretion processes around black holes create some of the most extreme physical conditions in the universe, with matter heated to billions of degrees and accelerated to significant fractions of the speed of light. These conditions forge new elements through nuclear processes, create intense magnetic fields that can accelerate particles to cosmic ray energies, and generate electromagnetic radiation across the entire spectrum from radio waves to gamma rays. The jets produced by spinning black holes can extend for millions of light years, carrying energy and processed matter far beyond their host galaxies. These jets interact with the intergalactic medium, heating it, stirring it, and enriching it with heavy elements forged in the extreme environments near the black hole. In this way, black holes serve as cosmic engines that process and redistribute matter throughout the universe. But there's something even more profound about the role of black holes in cosmic evolution. Some theories suggest that these objects might be necessary for the emergence of complexity and life in the universe. The feedback processes they create regulate star formation, preventing galaxies from using up their gas too quickly and ensuring a steady supply of new stars over billions of years. Without this regulation, galaxies might exhaust their star-forming material early in cosmic history, leading to a universe filled with old, dead stellar systems incapable of supporting the long-term evolution of complex structures like planets and life. Black holes, by controlling the pace of cosmic evolution, might be essential for creating the conditions necessary for complexity to emerge and flourish. The relationship between black holes and the formation of heavy elements is particularly important for the possibility of life. The extreme conditions near black holes can create nuclear processes that forge elements heavier than iron, which cannot be produced in the cores of ordinary stars. These heavy elements, distributed throughout the universe by black hole jets and outflows, provide the raw materials for rocky planets and the complex chemistry that underlies biological processes. Speaking of biological processes, let's explore the speculative but fascinating possibility that black holes might play a role in the evolution of life and intelligence throughout the universe. If advanced civilizations can learn to harness the energy stored in rotating black holes, these objects might become the power sources for galaxy-spanning civilizations. The amount of energy available from a rotating black hole is truly staggering. A supermassive black hole spinning at near maximum rate could potentially provide enough energy to power a civilization for billions of years, far longer than any individual star could sustain. This energy could be extracted through the Penrose process or through more exotic mechanisms that we haven't yet discovered. Some futurists have speculated that the ultimate fate of intelligence in the universe might be to migrate toward black holes, using them as both energy sources and information processing systems. The time dilation effects near black holes could allow civilizations to stretch their subjective lifespans enormously, experiencing eons of subjective time while the outside universe ages only briefly. In the far future, when the stars have burned out and the universe has grown cold and dark, black holes might be the only remaining sources of energy available to sustain complex structures like life and consciousness. Civilizations that learn to exist near black holes could potentially survive until the very end of the universe, watching the cosmos evolve through its final stages while maintaining islands of organization and complexity in the growing sea of entropy. But there's something deeply poetic about this possibility. It would mean that black holes, which appear to be the ultimate destroyers, the cosmic entities that consume everything in their path, might actually be the ultimate preservers, the final refugees where consciousness and complexity can persist long after everything else has faded away. Let's turn our attention to some of the more exotic theoretical possibilities that emerge from black hole physics. One of the most intriguing is the concept of black hole mining, the extraction of information and energy from these gravitational giants using advanced technology that we can barely imagine. If black holes do indeed store vast amounts of information on their event horizons, then it might be possible for sufficiently advanced civilizations to read and decode this information, essentially mining the memories of everything that has ever fallen into the black hole. This would make black holes into cosmic libraries, preserving the history of their regions of the universe in exquisite detail. The practical challenges of such an endeavour would be enormous. The information would be encoded in incredibly subtle patterns of Hawking radiation, or in the microscopic structure of the event horizon itself. Decoding it would require technology far beyond our current capabilities, perhaps involving quantum computers larger than planets or detection systems sensitive enough to measure individual quantum fluctuations. But if such technology could be developed, it would provide access to historical records spanning billions of years, including the complete quantum states of everything that ever fell into the black hole. Advanced civilizations might be able to reconstruct lost worlds, extinct species, even individual consciousness patterns preserved in the black hole's information storage system. Another exotic possibility is the creation of artificial black holes for various technological purposes. While creating stellar mass black holes would require enormous amounts of energy and matter, microscopic black holes might be within the reach of advanced civilizations. These tiny objects could serve as incredibly dense energy storage systems, waste disposal units for dangerous materials, or even as exotic matter sources for advanced propulsion systems. The evaporation of small artificial black holes could provide precisely controlled energy release, making them ideal power sources for applications requiring enormous amounts of energy in small volumes. The Hawking radiation from evaporating micro-black holes would be incredibly hot and energetic, potentially useful for driving advanced forms of spacecraft propulsion or for powering industrial processes that require extreme temperatures. Meanwhile, the theoretical possibility of naked singularities, regions where the normal space-time structure breaks down but isn't hidden behind an event horizon, opens up even more exotic possibilities. If naked singularities could be created or accessed, they might serve as gateways to regions where the normal laws of physics don't apply, potentially allowing for faster-than-light travel, time travel, or access to alternate dimensions. Of course, most physicists believe that the cosmic censorship hypothesis prevents naked singularities from forming in nature, protecting the universe from the unpredictable behavior that might emerge from these regions where physical law breaks down. But if this protection could be overcome through advanced technology, the possibilities would be truly limitless. Let's explore the connection between black holes and the deepest questions of cosmology and metaphysics. These objects force us to confront fundamental questions about the nature of reality, causality, and existence itself. They represent the extreme limits of physical law, the boundaries where our current understanding breaks down and new physics must emerge. The singularities at the centers of black holes represent what physicists call a breakdown of predictability. Beyond these points, our equations cease to provide meaningful answers, and we enter realms where space and time themselves might lose their familiar properties. Some theories suggest that singularities might be doorways to other dimensions or alternate universes, while others propose that they represent the fundamental limits of what can be known or described. The information paradox associated with black holes touches on deep philosophical questions about the nature of information and its relationship to reality. If information is truly fundamental, as quantum mechanics suggests, then the apparent destruction of information by black holes would represent a violation of one of the most basic principles of physics. But if information is preserved in ways we don't yet understand, it suggests that reality might be far more subtle and interconnected than we currently realize. The holographic principle emerging from black hole physics challenges our most basic assumptions about the dimensionality of space. If our three-dimensional experience is indeed a projection from information encoded on two-dimensional surfaces, then the solid, substantial reality we perceive around us might be nothing more than a cosmic illusion, albeit a remarkably persistent and detailed one. These ideas connect to ancient philosophical questions about the nature of reality and appearance, the relationship between the one and the many, and the possibility that our ordinary experience might be fundamentally misleading. Black holes, as the most extreme manifestations of gravitational physics, might be cosmic keys that unlock insights into the deepest structures of existence itself. The observer dependence revealed by black hole physics also raises profound questions about the nature of objectivity and truth. If different observers can have equally valid but contradictory descriptions of the same physical process, then the idea of a single, objective reality independent of observation might need to be abandoned. This would represent a return to more ancient ways of thinking about the relationship between mind and world, where consciousness plays a fundamental role in shaping the reality it observes. Meanwhile, the possibility that black holes might spawn new universes connects to cosmological questions about the origin and ultimate fate of our cosmos. If the Big Bang itself emerged from a black hole in a parent universe, then our entire reality might be just one branch of an infinite tree of cosmic evolution, with each black hole potentially giving birth to countless new worlds. This multiverse cosmology would mean that the formation of black holes isn't just a local phenomenon affecting individual stars and galaxies, but a fundamental process driving the evolution of reality itself. Every massive star that collapses would be planting seeds for future universes, each with its own physical laws, its own potential for complexity and consciousness. Let's delve deeper into the mathematical beauty and elegance of black hole solutions to Einstein's field equations. The Schwarzschild solution, discovered just months after Einstein published his theory of general relativity, represents one of the most beautiful and profound mathematical discoveries in the history of science. In just a few lines of equations, it describes the complete space-time geometry around a spherically symmetric, non-rotating massive object. But the true beauty of this solution became apparent only gradually, as physicists began to understand its physical implications. The solution naturally contains the concept of an event horizon, the boundary beyond which escape becomes impossible. Even though Schwarzschild himself didn't fully understand this aspect of his discovery, it wasn't until decades later that physicists realized they were looking at a description of objects that would later be called black holes. The Kerr solution, describing rotating black holes, adds layers of mathematical complexity that reveal new depths of physical meaning. The rotation creates frame-dragging effects that twist space-time itself, generating new regions like the ergosphere, where the geometry of reality becomes even more exotic. The mathematics of Kerr black holes involves complex coordinate systems and intricate relationships between mass, angular momentum, and space-time curvature that challenge our geometric intuition. These solutions demonstrate that mathematics isn't just a tool for describing reality, but seems to capture something essential about the structure of the universe itself. The equations of general relativity, when pushed to their limits in the extreme gravitational fields of black holes, reveal phenomena that no human mind could have imagined without the guidance of mathematical insight. The study of black hole thermodynamics has revealed deep mathematical connections between gravity, quantum mechanics, and information theory. The Bekenstein-Hawking entropy formula, relating the entropy of a black hole to the area of its event horizon, suggests that the fundamental units of information in the universe might be much larger than previously thought. Each unit of black hole entropy corresponds to an area equal to 4 times the Planck area, the smallest meaningful area, in quantum gravity. This quantization of area and entropy suggests that spacetime itself might be granular at the smallest scales, composed of discrete units rather than forming a smooth continuum. The implications for our understanding of quantum gravity are profound, suggesting that space and time might emerge from more fundamental discrete structures in ways we're only beginning to understand. Meanwhile, the mathematical structure of black hole solutions reveals deep symmetries and conservation laws that connect to the most fundamental principles of physics. The no-hair theorem demonstrates that black holes can be characterized by just 3 parameters: mass, electric charge, and angular momentum. All other information about their formation history is erased, leading to objects of remarkable simplicity emerging from the collapse of complex stellar systems. This simplicity is both elegant and troubling. It suggests that black holes represent the ultimate limit of compression and organization, reducing the infinite complexity of stellar matter to just a few numbers. But it also raises questions about information loss and the reversibility of physical processes, contributing to the information paradox that continues to challenge our understanding of quantum gravity. Let's explore the relationship between black holes and the concept of emergence. The idea that complex systems can exhibit properties and behaviors that aren't present in their individual components. Black holes might be the ultimate examples of emergent phenomena, where the collective behavior of vast numbers of particles creates entirely new physics that transcends the properties of individual atoms and molecules. The event horizon itself is an emergent structure that exists only when matter is compressed beyond a critical density. Individual particles don't have event horizons, but when enough matter is gathered together in a small enough volume, the collective gravitational field creates this boundary that changes the causal structure of space-time itself. The thermodynamic properties of black holes, their temperature and entropy, are also emergent phenomena that arise from the collective behavior of quantum fields in curved spacetime. These properties aren't present in classical general relativity, but emerge when quantum mechanics is taken into account, revealing new layers of physics that weren't apparent in the original theory. The holographic principle suggests that black hole physics might provide insights into emergence more generally, showing how higher dimensional phenomena can emerge from information processing on lower dimensional boundaries. If our 3-dimensional reality is indeed emergent from 2-dimensional information processing, then consciousness, complexity, and all the richness of experience might be emergent properties arising from more fundamental information theoretic processes. This connects to broader questions about the relationship between reductionism and emergence in science. While physics has traditionally sought to understand complex phenomena by reducing them to simpler components, black hole physics suggests that some properties might be irreducibly emergent, requiring new conceptual frameworks that can't be derived from the behavior of individual parts. Speaking of emergence, let's consider the possibility that consciousness itself might be related to the information processing capabilities of black holes. Some researchers have speculated that the universe might be fundamentally computational, with physical processes serving as information processing operations on a cosmic scale. If this is correct, then black holes, as the most extreme information processing systems in the universe, might represent cosmic computers capable of calculations far beyond anything we can imagine. The entropy of a supermassive black hole represents an information storage capacity that dwarfs any computer we've ever built, suggesting that these objects might be capable of computational feats that would seem magical by our current standards. The idea that consciousness might be related to information integration in complex systems suggests that black holes might possess some form of awareness or experience. This doesn't necessarily mean they're conscious in the same way that humans are, but it raises the intriguing possibility that information processing itself might be associated with some form of subjective experience. Of course, this remains highly speculative, and consciousness might require specific types of information processing that only occur in biological systems. But the possibility highlights how black hole physics is forcing us to reconsider fundamental questions about the relationship between mind and matter, between information and experience. The integrated information theory of consciousness proposes that awareness arises from the integration of information across complex networks. By this measure, a supermassive black hole, with its vast entropy and complex internal structure, might possess more integrated information than any biological brain. If consciousness is indeed related to information integration, then these cosmic giants might be conscious in ways that we can barely comprehend. Let's explore the practical implications of black hole research for future space exploration and technology development. While black holes themselves are far too dangerous to approach directly with current technology, the insights gained from studying them have already begun to influence our thinking about advanced propulsion systems, energy generation, and space-based civilizations. The extreme time dilation effects near black holes could potentially be exploited by advanced civilizations for various purposes. Time dilation allows for a form of time travel into the future, where travelers could experience days or weeks while centuries or millennia pass in the outside universe. This could be useful for long-term space exploration, allowing crews to survive journeys to distant galaxies that would otherwise take longer than human lifespans. But the practical challenges of utilizing black holes for time dilation would be enormous. The tidal forces near black holes strong enough to produce significant time dilation would be fatal to any biological organism, requiring advanced technology to survive. The energy requirements for escaping from such deep gravitational wells would be staggering, potentially requiring the complete conversion of matter to energy through processes we don't yet understand. The concept of black hole starships, spacecraft powered by artificial micro-black holes, has been explored by theoretical physicists and science fiction writers alike. Such systems could potentially provide enormous amounts of energy in very small volumes, making them ideal for interstellar propulsion. The controlled evaporation of micro-black holes could provide thrust through the emission of Hawking radiation, creating rockets with specific impulses far exceeding any chemical or nuclear propulsion system. However, creating and controlling micro-black holes would require technology far beyond our current capabilities. The energy required to compress matter to black hole densities is enormous, and maintaining control over an evaporating black hole would require precise manipulation of quantum fields in ways we're only beginning to understand theoretically. The gravitational wave signatures of black hole mergers provide new ways of studying the universe and could potentially be exploited for communication across galactic distances. Gravitational waves travel at the speed of light and can pass through matter without absorption, making them ideal for long-range communication in a universe filled with dust, gas, and other obstacles to electromagnetic signals. Advanced civilizations might learn to generate artificial gravitational waves using controlled black hole systems, creating a cosmic internet that spans the galaxy. The information-carrying capacity of gravitational waves is enormous, potentially allowing for the transmission of complete virtual realities across interstellar distances. Meanwhile, the study of accretion disks around black holes has revealed new insights into plasma physics, magnetic field dynamics, and high-energy particle acceleration that could be applied to fusion power generation and advanced propulsion systems. The magnetic fields around black holes can accelerate particles to near light speed, suggesting new mechanisms for achieving controlled fusion reactions or for creating high-energy particle beams for propulsion. Let's delve deeper into the connection between black holes and the ultimate fate of the universe. Current cosmological models suggest that the universe is expanding and cooling, eventually reaching a state where all the stars have burned out and only black holes remain. In this far future scenario, black holes become the dominant objects in the cosmos, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. The evaporation process is incredibly slow for large black holes. A black hole with the mass of our Sun would take longer than 10 to the 67th power years to evaporate completely, a timescale so vast that it's almost meaningless to human comprehension. The supermassive black holes at galaxy centers would take even longer, persisting until the universe is unimaginably old and cold. But eventually, even the largest black holes will evaporate, leaving behind only elementary particles and radiation in an expanding, cooling universe. This represents one possible ultimate fate for our cosmos, a heat death where all complex structures have dissolved and the universe has reached maximum entropy. However, some theories suggest that black hole evaporation might not represent the end of complexity, but could potentially seed new forms of organization. The final stages of black hole evaporation release enormous amounts of energy in very short time periods, potentially creating conditions where new physical processes become possible. Some speculative theories propose that the evaporation of primordial black holes, tiny black holes that might have formed in the early universe, could be responsible for dark matter or could provide the seeds for new phases of cosmic evolution. These ideas remain highly speculative, but they suggest that black holes might play important roles in cosmic evolution that we're only beginning to understand. The possibility that black holes might spawn new universes through quantum tunneling or other exotic processes offers an alternative to heat death. In this scenario, the apparent end of our universe through black hole evaporation might actually be a transformation into new forms of reality that we can't currently imagine. This connects to broader questions about the cyclical nature of cosmic evolution. If universes can be born from black holes, then cosmic evolution might be an endless cycle of birth, growth, collapse and rebirth, with each generation of universes potentially exploring new physical laws and new possibilities for complexity and consciousness. Let's explore the philosophical implications of black hole physics for our understanding of knowledge, truth, and the limits of scientific inquiry. These objects represent boundary cases where our current theories break down and new physics must emerge, forcing us to confront the limits of what can be known through observation and experiment. The event horizons of black holes create absolute limits to observation, regions of space-time that are forever cut off from outside observers. This represents a fundamental limitation to empirical knowledge, suggesting that there might be aspects of reality that are permanently inaccessible to scientific investigation. But this limitation might not be as restrictive as it initially appears. Theoretical physics has shown that we can infer a great deal about the interiors of black holes through indirect means, using mathematical consistency, symmetry principles, and quantum mechanical arguments. The information paradox itself arises from our theoretical understanding of what must happen inside black holes, even though we can never directly observe these processes. This suggests that human knowledge might be able to transcend the apparent limits imposed by physical boundaries through the power of mathematical reasoning and theoretical insight. The fact that we can contemplate and analyze the information paradox, even though it involves processes we can never directly observe, demonstrates the remarkable reach of human intellect. The observer dependence revealed by black hole physics also raises deep questions about the nature of scientific objectivity. If physical processes can have multiple, equally valid descriptions depending on the reference frame of the observer, then the goal of finding a single objective description of reality might need to be abandoned in favor of a more pluralistic approach to truth. This doesn't necessarily mean that truth becomes relative or arbitrary, but rather that reality itself might be fundamentally perspectival, with different aspects becoming apparent to different types of observers. the challenge for science becomes not just describing what happens, but understanding how different descriptions relate to each other and what they reveal about the underlying structure of reality. Meanwhile, the mathematical beauty and elegance of black hole solutions to Einstein's equations suggest that aesthetic considerations might play a fundamental role in physics. The fact that the most profound insights into the nature of gravity come from solutions that are mathematically beautiful hints at deep connections between truth and beauty that we're only beginning to understand. This connects to ancient philosophical ideas about the relationship between goodness, truth, and beauty, suggesting that these concepts might be more intimately connected than modern science has typically assumed. The study of black holes, by pushing physics to its limits, might be revealing aspects of reality that transcend the traditional boundaries between science, mathematics, philosophy, and art. As we continue our journey through the strange landscape of black hole physics, it's worth reflecting on how these objects challenge our most basic assumptions about the nature of existence. They force us to confront questions about the relationship between something and nothing, between existence and non-existence, between knowledge and ignorance. The singularities at the centers of black holes might represent the closest thing to absolute nothingness that exists in our universe, points where the familiar properties of matter, energy, space, and time all break down. Yet these regions of nothingness are also the most massive, most gravitationally influential objects in the cosmos, suggesting that nothing and something might be more intimately connected than we normally suppose. The information paradox raises similar questions about the relationship between existence and non-existence. If information falling into a black hole is truly destroyed, then something can indeed become nothing, violating one of the most fundamental principles of physics. But if information is preserved in subtle ways we don't yet understand, then the apparent destruction might be an illusion, and the something continues to exist in forms we can't currently perceive. These questions connect to the deepest mysteries of consciousness and existence. What does it mean for something to exist? Is existence binary, a simple matter of being or not being, or are there gradations and subtleties that our ordinary thinking misses? Black holes, by existing at the boundary between something and nothing, might provide insights into the nature of existence itself. The possibility that our three-dimensional reality is emergent from two-dimensional information processing suggests that existence itself might be emergent, arising from more fundamental processes that don't necessarily have the properties we associate with reality. If the holographic principle is correct, then the solid, substantial world we experience might be a kind of cosmic projection, real in its own way but not fundamental. This brings us to questions about the nature of consciousness and its relationship to physical reality. If space-time itself is emergent from information processing, then consciousness, as another information processing phenomenon, might be more fundamental than we typically assume. Rather than consciousness emerging from matter, matter itself might emerge from information processing activities that have consciousness as their most basic feature. Of course, these ideas remain highly speculative, and we're still far from understanding the deep connections between physics and consciousness. But black holes, as the most extreme manifestations of physical law, continue to provide new perspectives on these ancient questions, suggesting that the boundaries between physics and philosophy might be more porous than we commonly assume. In the stillness of night, when the world softens and slows, it's worth contemplating how black holes embody both the ultimate expression of cosmic violence and the deepest form of cosmic mystery. These objects represent destruction and creation, endings and beginnings, isolation and connection. They're cosmic monsters that devour everything in their path, yet they might also be cosmic gardeners that nurture and shape the very galaxies they inhabit. The story of black holes is really the story of how the universe processes information, how complexity arises from simplicity, and how consciousness emerges from the quantum mechanical substrate of reality. These objects, which appear to be the ultimate destroyers, might actually be the ultimate preservers, encoding and processing the information that falls into them in ways we're only beginning to understand. As you drift towards sleep, consider that every atom in your body, Every thought in your mind, every moment of your experience might someday fall into one of these gravitational giants, becoming part of the cosmic information processing system that spans the universe. Your consciousness, your memories, your dreams might all be preserved in the quantum structure of space-time itself, encoded in patterns that persist long after the stars have burned out and the universe has grown cold. This is not a frightening prospect, but a beautiful one, suggesting that consciousness and complexity are fundamental features of reality, rather than temporary accidents. The universe, through its black holes and quantum processes, might be a vast information processing system, a cosmic mind of which we are all temporary but eternal parts. The mathematics of black holes, with their event horizons and singularities, their temperature and entropy, their quantum fluctuations and holographic projections, reveals a universe far stranger and more wonderful than our everyday experience suggests. It's a cosmos where time and space are fluid, where information is fundamental, and where consciousness might play a central role in shaping the reality it observes. As we've explored together tonight, black holes challenge every assumption we might make about the nature of existence. They show us that the universe is not a collection of separate objects sitting in empty space, but a unified field of information and energy, where every part is connected to every other part through quantum entanglement and gravitational influence. The journey we've taken through black hole physics tonight has revealed layer after layer of mystery and wonder. We've seen how these objects emerge from the depths of massive stars, creating regions where space-time curves so dramatically that it closes in on itself. We've explored how they challenge our understanding of time, causality, and information, forcing us to reconsider the most basic assumptions about reality. We've discovered that black holes aren't just cosmic vacuum cleaners, but are complex thermodynamic systems with temperature and entropy, capable of information processing on scales that dwarf any computer we've ever imagined. We've seen how they regulate the formation of stars and galaxies, serving as cosmic gardeners that shape the evolution of structure throughout the universe. The quantum mechanics of black holes has revealed connections between gravity and information theory that are transforming our understanding of both physics and consciousness. The holographic principle suggests that our familiar three-dimensional reality might be a projection from information encoded on distant surfaces, while the information paradox challenges us to reconsider the relationship between knowledge and existence. We've contemplated the possibility that black holes might be conscious entities, processing information in ways that create subjective experience on cosmic scales. We've explored how they might serve as gateways to other universes, spawning new realities through processes we can barely imagine. We've seen how they embody both destruction and creation, serving as the ultimate recyclers of matter and energy in the cosmic economy. The mathematical beauty of black hole solutions to Einstein's equations reveals deep connections between truth and beauty, between physical law and aesthetic principle. These objects demonstrate that the universe is fundamentally mathematical in nature, with equations capturing aspects of reality that no amount of direct observation could reveal. As we've journeyed together through these cosmic mysteries, we've seen how black holes force us to confront the limits of knowledge and the nature of existence itself. They represent boundary cases where our current theories break down, revealing the need for new physics that can bridge the gap between quantum mechanics and general relativity. The observer dependence revealed by black hole physics suggests that reality itself might be fundamentally perspectival, with different aspects becoming apparent to different types of observers. This challenges our notion of objective truth while opening up new possibilities for understanding the relationship between consciousness and physical reality. Throughout this exploration, we've been reminded again and again that the universe is far stranger and more wonderful than our everyday experience suggests. Black holes reveal a cosmos where time dilates and space curves, where information is fundamental and consciousness might play a central role in shaping reality. These insights connect to the deepest questions of existence and meaning. If black holes do indeed preserve information through holographic encoding, then every moment of experience, every thought and feeling might be eternal aspects of the cosmic information processing system. The temporary patterns we call consciousness might be part of a vast ongoing computation that spans the entire universe. The possibility that our reality is emergent from more fundamental information processing suggests that consciousness isn't just an accidental byproduct of complex matter, but might be intrinsic to the basic structure of existence. We might not just be observers of the universe, but active participants in its ongoing creation and evolution. As you prepare to sleep, consider that the atoms in your body were forged in the hearts of dying stars, the same stars whose collapse created the black holes we've been exploring. The carbon in your cells, the oxygen you breathe, the iron in your blood, all were created through stellar nuclear synthesis and distributed throughout the cosmos by the very processes that give birth to black holes. You're quite literally made of star stuff, connected through cosmic evolution to the most exotic objects in the universe. The black holes we've contemplated tonight are not alien entities separate from human experience, but are part of the same cosmic story that includes your existence, your consciousness, your capacity for wonder and understanding. The quantum fields that create Hawking radiation around black holes are the same fields that give rise to the particles in your body. The space-time that curves around these gravitational giants is the same space-time through which you move and in which you exist. The information processing that might occur in black holes is related to the information processing that creates your thoughts and experiences. In this sense, exploring black holes is a form of self-discovery, a way of understanding the cosmic context from which consciousness emerges. These objects reveal not just the physics of extreme gravity, but the deep connections between mind and matter, between local experience and cosmic evolution. The mathematical elegance of black hole physics suggests that the universe is fundamentally comprehensible, despite its strangeness and complexity. The fact that human minds can contemplate and understand these exotic objects, at least partially, reveals something profound about the relationship between consciousness and cosmos. We are pattern recognition systems that emerge from the cosmic evolution that includes black hole formation. Our ability to understand these objects suggests that consciousness and cosmos are intimately related, perhaps two aspects of a deeper underlying reality that transcends the traditional boundaries between subject and object, mind and matter. As we reach the end of our cosmic journey tonight, it's worth reflecting on the sense of wonder and mystery that black holes inspire. These objects represent the frontiers of human knowledge, the boundaries where our current understanding meets the unknown. They remind us that despite all our scientific progress, the universe still holds secrets that challenge our deepest assumptions about the nature of reality. But rather than being discouraging, this mystery is profoundly inspiring. It suggests that the cosmos is inexhaustible, that there will always be new discoveries to make, new puzzles to solve, new perspectives to gain on the nature of existence. Black holes represent not the limits of knowledge, but invitations to expand our understanding, to develop new theories and new ways of thinking about reality. The journey through black hole physics we've taken tonight reveals a universe that is simultaneously more strange and more beautiful than we could have imagined. These objects show us that reality operates according to principles that transcend our everyday experience, while remaining fundamentally mathematical and comprehensible to conscious minds. They demonstrate that the cosmos is not a mechanical clockwork, but a dynamic, evolving information processing system where consciousness might play a fundamental role. They suggest that our existence is not accidental, but is intimately connected to the deepest structures and processes of reality itself. In the quiet moments before sleep, when thoughts become soft and meandering, you might find yourself contemplating the vast scales of space and time that black holes represent. These objects connect us to cosmic processes that operate on scales from the quantum to the galactic, from microseconds to eons, from individual particles to entire universes. They remind us that we exist within a cosmic story that includes stellar birth and death, galaxy formation and evolution, the emergence of complexity and consciousness. Our brief human lives are temporary patterns in this vast cosmic dance, but patterns that are capable of understanding and appreciating the beauty and mystery of the whole. The fact that black holes exist, that they follow mathematical laws we can discover and understand, that they reveal deep connections between apparently separate aspects of physics, suggests that the universe is not only comprehensible, but is structured in ways that make consciousness and understanding possible. This is perhaps the most profound insight to emerge from our exploration of black holes tonight. These objects, which might seem to represent the ultimate in alien incomprehensibility, actually reveal deep patterns and principles that connect directly to human experience and understanding. They show us that we are not separate from the cosmos but are intrinsic parts of its ongoing evolution and self-understanding. As you drift towards sleep, carried by thoughts of event horizons and quantum entanglement, of space-time curvature and information paradoxes, remember that all of these exotic phenomena are aspects of the same reality that includes your consciousness, your capacity for wonder, your ability to find beauty and meaning in the mathematical structures that govern cosmic evolution. The universe that contains black holes is the same universe that contains love and friendship, art and music, hope and joy. The quantum fields that create Hawking radiation are the same fields that make possible the electrochemical processes of thought and feeling. The information processing that might occur in cosmic-scale black holes is related to the information processing that creates your memories, your dreams, your sense of self and connection to others. In this grand cosmic context, black holes are not just exotic objects to be studied, but are revelations of the deep unity that underlies apparent diversity, the fundamental connectedness that links conscious experience to cosmic evolution. They remind us that we are participants in a cosmic story of unimaginable scope and beauty, temporary but eternal patterns in the ongoing dance of matter, energy, space, time, and consciousness. Tonight, as you rest in the knowledge that you are made of star stuff and connected through quantum entanglement to the farthest reaches of space and time, may your dreams be filled with the wonder and mystery of these cosmic giants. May you find peace in knowing that your consciousness is part of the same information processing system that spans the universe, encoding and preserving every moment of beauty, every insight into truth, every expression of love and compassion. The black holes we've explored together will continue their cosmic dance long after our individual patterns of consciousness have dissolved back into the quantum foam from which they emerged. But the insights we've gained, the wonder we've experienced, the connections we've discovered between mind and cosmos, these become part of the eternal information structure of the universe itself. In the vast library of cosmic information that black holes might represent, every moment of conscious experience, every recognition of beauty, every glimpse of truth becomes part of the permanent record of what it means to be aware in a universe capable of understanding itself. Your thoughts tonight, your sense of wonder at the mysteries we've explored, your growing appreciation for the deep connections between consciousness and cosmos all become part of this eternal cosmic memory. So rest well, knowing that you are part of something infinitely larger and more beautiful than individual existence, yet something that requires conscious observers like yourself to be complete. The universe needs minds capable of wonder and understanding to fulfill its potential for meaning and beauty. In contemplating black holes tonight, you have participated in the cosmic process of self-understanding, helping the universe come to know itself through conscious reflection and scientific inquiry. May your sleep be peaceful and your dreams be filled with the gentle wonder of cosmic mysteries. May you wake refreshed and renewed, carrying with you a sense of connection to the vast scales of space and time, the deep patterns of mathematical beauty, and the profound mystery of consciousness arising from quantum fields and curved space-time. The black holes we've explored tonight will continue their eternal dance, processing information, shaping galaxies, and perhaps spawning new universes filled with new possibilities for complexity and awareness. In their cosmic recycling of matter and energy, in their preservation and transformation of information, in their role as both destroyers and creators, they embody the fundamental processes that make consciousness and understanding possible. Thank you for joining me on this journey through the cosmic mysteries of black holes. Thank you for your curiosity, your patience with complex ideas, and your willingness to contemplate the deepest questions about the nature of existence. It's been a privilege to explore these profound mysteries together, to share in the wonder and beauty of cosmic evolution, and to consider how our consciousness connects us to the vast processes that shape the universe itself. If this gentle journey through the physics of black holes has filled you with wonder about the nature of reality, if it has helped you see connections between your existence and the cosmic processes that span space and time, if it has brought you a sense of peace and perspective on your place in the vast scheme of things, then our time together has been well spent. I hope you'll continue to carry this sense of cosmic connection with you, remembering that you are part of a universe far more strange and beautiful than everyday experience suggests. The insights of modern physics reveal that reality is fundamentally mysterious and wonderful, filled with connections and possibilities that transcend the boundaries of ordinary perception. Sweet dreams, and may you rest peacefully in the knowledge that consciousness and cosmos are intimately connected, that your capacity for understanding and wonder makes you a participant in the universe's ongoing journey of self-discovery. May your thoughts be soft and your sleep come easy, carried by the gentle rhythms of cosmic evolution and the profound mystery of awareness arising from the quantum mechanical foundation of reality. And just as we began, let me remind you that this exploration has been for relaxation and wonder, not as any form of scientific or medical advice. Always take care of yourself. Keep your consciousness safely anchored in the here and now, and sleep well under the vast canopy of stars that includes countless black holes continuing their eternal cosmic dance.